In this section, we're going to take a look at one of the ways that we can use derivative to analyze the nature of a graph, whether or not we see the graph. You see, we can actually look at an algebraic form and know a great deal about the behavior of the graph. Now, let's first of all, though, look at a graph and the graph of the derivative function and notice a couple of things. First of all, here's the function, and here is the graph of the derivative function. Now, here's what I want to point out. In this region of the graph is increasing from left to right. We're always thinking left to right, and the graph is going up, it's rising, so it's increasing. And in the interval from -2 to 2, the graph is decreasing. And then in the interval from 2 to infinity, it's increasing once again. Now, what does that mean in terms of derivative? Well, think about slope of the tangent line for a moment. Now, in this region, the slope of the tangent line is a positive value. Positive, positive, all the way up to this point right at the top. And by the way, the derivative at that point, you see the slope of that tangent line would be 0, wouldn't it? And then it turns negative. You see the slope of that tangent line turns negative and is negative throughout this interval in which the graph is decreasing. And then when the graph goes into this increasing idea once again, we have the slope of the tangent line positive once again. Now let's see how that looks on the graph of the derivative function. Now we would expect that in this region, in this interval from -infinity to -2, that because the graph is increasing, we have a positive slope, and do we not have positive values in that derivative function? Oh, yes we do. You see the y values are above the x-axis, and so the function is positive throughout this interval. And then in the interval in which the graph of the function is decreasing, we have the derivative function is negative throughout that interval. And then in the interval where the function is increasing once again, the derivative is positive, the slope of the tangent line is positive in this region, and it is no wonder then that the derivative function is positive in that interval as well. Well, those are aspects that we want to notice here, and we want to figure out how algebraically we can identify these various regions. Well, let's take a rather formal approach now to the notion of increasing and decreasing. Now, graphs can actually be increasing, decreasing, or constant. If a graph is constant, it just means that it sort of flatlines. It's y equals 7 or something like that, and so we have a horizontal line. But the increasing and decreasing ideas are the ones that are most important to us. And in a rather formal way, if x sub 1 is greater than x sub 2, then f of x sub 1 is greater than f of x sub 2. Sounds mysterious, doesn't it? Well, let's take the mystery out of it by looking at these points. X sub 1 is greater than x sub 2. A point is greater than another point. All right, let's come over here. Now, in this interval, we have a point, let's say here, that's greater than that point. And it says that this implies that f of x sub 1, f of this function, oh, it's up here, is greater than, is higher than f of that x sub 2. You see. And then the opposite holds true when we're in this region. That is, formally it says if x sub 1 is greater than x sub 2, that implies that f of x sub 1 is less than f of x sub 2. Okay, x sub 1 is greater than x sub 2. Here's x sub 1, here's x sub 2. X sub 1 is greater than x sub 2. F of x sub 1, you see, is less than f of x sub 2. You see, that's the idea. So algebraically, we can identify this idea of increasing and decreasing using these ideas. Okay, now here's the interesting part. In an interval a to b, if it turns out that throughout this interval that the derivative function is positive, then the function itself is increasing. And if in that interval the derivative function is negative, then f is decreasing. And if the derivative function is 0, you see, then that's the situation. Slope of the tangent line is 0, and therefore we have a horizontal situation and for that tangent line, and therefore f is constant. Okay, now, how do we make these decisions? How do we make these discoveries if we're just looking at algebraic forms? Well, here's how we do that. Now, this is the function of the first graph over here. And notice that, gee, it has a fraction in it and so forth. But here's how we go through the analysis process. We first take the function and we want its derivative. So I'm going to change it a little bit to make it easier to take the derivative. I'm going to write this as 1/4 x cubed and then minus 3x. So taking the derivative, and we remember how to do that. 3 times the 1/4 is 3/4. 1 less than 3 is 2, and this is minus 3. Okay. Now, so here's the derivative function. Now, what we'd like to do at this point is identify the zeros of this function, or those values that may be undefined for the function. Now, to find the zeros, we do this. We just set this expression equal to 0 and solve this for x. All right, well, to solve for x, gee, I see a fraction. I can clear it rather easily by multiplying through by 4. Multiply this term by 4, I get 3x squared. Multiply this by 4, I get negative 12. Snag out a common factor of 3, and I have x squared minus 4. Oh, difference of squares. So we have x plus 2 times x minus 2. So x equals 2, x equals negative 2 are the zeros for the derivative function. Now, these are important positions. Remember, these zeros of the derivative function are the place where the slope of the tangent line is 0. Now, these have special significance graphically, but we call them critical numbers because they are places where it's possible that the graph is changing from increasing to decreasing. Now, here's how we find out. We take these critical numbers and we imagine them on a number line, and these two numbers would actually, these 2 points on a number line would actually separate the number line into 3 regions, 3 intervals, and I've identified them here. Now, you can see them clearly like this. If I draw a number line, and this is negative 2, and let's say this is 2, then the intervals are the interval out here, the interval between, and the interval over here. Now, the interval to the left of negative 2 is the interval from negative infinity to negative 2. So that's why I've put negative infinity to negative 2. Then the interval between them is negative 2 to 2. And then out here would be 2 to infinity. Now, notice that I'm using an open interval for each of these intervals. And we can get technical with that idea a little bit if we want to, but just for right now, just use open intervals. Now, here's what we do within those intervals. We want to analyze what's happening with the derivative function within that interval. For x values which are in the interval from negative infinity to negative 2, is the derivative function positive or negative? Now, we can choose a specific value, a specific number which is in the interval, and use it as a test point, or we can say something about it generally. Now, this interval contains big negative numbers, and that's the way I like to look at it, because really all we're doing is trying to figure out whether or not we have positiveness or negativeness for the numbers that are in that interval. And we can analyze it like this. Let's slide back over here and look at the derivative function. Now, in that interval, we have big negative numbers. Big negative numbers squared, those would be big positive numbers, and 3/4 of that would be still a big positive number, minus 3. Gee, this is going to be positive. So the derivative function is positive when x values fall in this interval. The derivative function is positive. That implies that in this interval, the graph of f is increasing. Now, f prime is positive, so it means that f is increasing in that interval. And that's what we found earlier. You see, we saw the graph. And in this interval, let's see, we identify a point in this interval if we want to. And I think when we have an interval that doesn't contain really, really big numbers or really, really big negative numbers, then we take a specific value, and the easiest one to choose in here would be 0. So let's decide whether the derivative function is positive or negative by plugging in 0 for x. If x is 0, this term goes out and we have negative 3. So the derivative function is negative in that interval, and therefore we know that the graph of f is decreasing. And over here in this interval from 0 to infinity, we're talking about really big numbers. And we come back over here and analyze the situation. Really big numbers squared, huge. 3/4 of that, still big. Minus 3, positive values. So the derivative function is positive for x values that lie in this interval. and therefore the graph of f is increasing in that interval. Well, I think it's important to know here, and we'll examine this in greater detail in a later section, but does it make some sense that if we have an interval here in which the graph of f is increasing, and right next door to it we have an interval in which the graph is decreasing, that should it make some sense that right on the border of these two, they're shoulder to shoulder here, you see, that right on the border of those two we have a situation where we have a relative maximum point. We're going to have a maximum point on the graph right in the at the connection, if you will, of these two intervals. And in a similar way, if we're decreasing from left to right and we go into an increasing situation, so we're decreasing and then we go increasing, graph is decreasing and then it goes increasing, gee, we have a relative minimum point, you see. And that's kind of an important consideration as well. We'll have a lot more to say about that as I mentioned before. All right, let's look at another graph. Now this one contains an interesting nuance. Remember I said that the critical values are the zeros of the derivative function. They also may be those values that are undefined in the derivative function. And this problem contains values like that. If this is our original function, then we take the derivative of the original function. And remember, it's 2/3 times this to an exponent 1 less than that. You see 2/3 minus 1 is negative 1/3 times the derivative of this business, which is 2x. Okay, now we'd like to clean that up a little bit. Now I've cleaned it all up in one step here. And maybe it would take more than one step if we were actually doing it on paper, but I don't have a lot of room here, and therefore I'm making these decisions. Now take a look at what I have. The negative exponent here sends this base down into the denominator. You see, so we have a binomial factor in the denominator, and this 3 is also in the denominator, so that's why these items appear here. This 2 is multiplied times that 2x to get 4x for the numerator. So that's where that stuff comes from. Now, the critical numbers are the zeros or undefined values involved in this expression. And let's see, the numerator becomes 0 when x itself is 0. So x equals 0 is a critical number. And let's see, for the denominator, you see the denominator can't become 0. We disallow the idea of denominators being 0 because that makes the fraction undefined. So undefined values would occur at the zeros of the denominator, and those occur when this binomial becomes 0 itself. And now let's see, this is x squared minus 4. X squared becomes 4 when x itself is either 2 or negative 2. So 2 and negative 2 then are also critical numbers. Now, by the way, there is another way to write this, and in fact the original problem as well. The 1/3 exponent implies a radical, so we could write this as the cube root of x squared minus 4 if we decide to do that. All right, let's pick up the problem from this point. We have critical numbers here, and then we identify the intervals into which these critical numbers subdivide our number line, if you will. So we have, let's see, 0, 2, and negative 2. If I came out here to the side and did this, and it doesn't take a very big sketch, but I want to identify these 3 values. You see, I have negative 2, I have 0, I have 2. So the intervals are this interval, that interval, this interval, that interval. And I just want to describe them using some form of interval notation. Now I'm using interval notation here. I think in your textbook you may see that interval described using inequalities, but it's the same idea. So this interval is from negative infinity to negative 2. This interval is from negative 2 to 0. This interval is from 0 to 2. And then this interval is from 2 to infinity. All right, let's, here are those intervals, and away we go. Now, we would probably do something like this, and we're making decisions about f prime in this interval. You see, so we're thinking about numbers which are big negatively here. Big negative number. Now what happens to the f prime function in this region? Well, a big negative number would cause this numerator to be negative, and a big negative number squared, oh, that's going to be a big positive number. minus 4, still positive. The cube root of that, still positive. So the denominator is positive while the numerator is negative. That gives us a fraction which is negative. So the derivative function is negative for x values that fall into this interval. So f prime of x then is less than 0. And that means then that the graph is decreasing. That is, the graph of the original function is decreasing in this interval. Now, in the interval from -2 to 0. Now, as I say, if we have a specific interval in which it's kind of tight here, it doesn't go to infinity, we can't just say big numbers or big negative numbers or something like that, we probably are wise to choose a value which is in the interval. So let's see, we might choose -1 as a test value. So -1 times 4, that makes this negative. -1 squared is 1. 1 minus 4, oh, that's -3. The cube root of -3 would be negative. Negative times 3 is negative. The denominator is also negative. So negative divided by negative, positive. The derivative function then is positive. And therefore, the graph is increasing. Now, the tendency at about this point is for students to think that, gee, this is just going to always alternate. It's always going to be the case that we have less than 0, greater than 0, less than 0, greater than 0, decreasing, increasing, decreasing, increasing. It might turn out that way on 20 problems, but it's not always that way. And that's why we need to deal with every one of these sort of as a separate event. So let's go through that. I'll show you an example like that in a little bit. But in this one, f prime of x, well, let's see, positive or negative. We're choosing values in this interval. 1 is a handy one to choose. If x is replaced with 1, we have 4 times 1, 4. Positive number in the numerator. 1 squared is 1. 1 minus 4, -3. -3, the cube root of -3. Oh, that's negative. Times 3, negative. Positive divided by negative, negative. So this is less than 0. A negative derivative in that interval means that we have a decreasing graph. And now we turn our attention to the next interval for x values in the interval from 2 to infinity. Well, we consider just very big positive numbers, and when we put big positive numbers into the numerator, we get a positive value. Big positive numbers squared, -4, positive cube root of that, positive times 3, positive, positive all over the place. So the derivative function then is positive for x values that lie in this interval, and we know then that the graph is increasing in that interval. Now, we know all of this information just from the analysis of the function and the derivative function. Now, we might want to go ahead and sketch the graph of this. You might want to pop this onto the graphing calculator and see what it looks like to verify all of this increasing and decreasing behavior of the graph. Here we have a third-degree polynomial function, and let's discover some aspects of its graph. We take the derivative of the function and we find it to be this. We'd like the zeros or undefined values associated with this function. So we'll set it equal to 0 and we take out a common factor of 3, and then we factor the trinomial into x minus 1 times x minus 1. There's only one 0 here, and it is x equals 1, and that's our critical number. And now that critical number subdivides the number line into a couple of intervals, the interval from -infinity to 1 and the interval from 1 to infinity. Now we examine what happens to the derivative function when an x value falls into these two intervals. Well, if a number is real big negatively, let's see what happens. A real big negative number, and by the way, I can examine the situation here or I can examine it up here. It really doesn't make too much difference. I think it's easier to examine here. We think of this as f prime of x equals this factored form. So if we have a real big negative number, -1, that's big negatively, and this would be big negatively. Negative times negative is positive. So this product is positive. So the derivative function is positive, and therefore the graph is increasing. Now we might think, well, gee, if it's increasing in this interval, it's probably decreasing over here, right? Well, not necessarily. Let's see what happens. Real big positive numbers occur in this interval. Big positive number minus 1, positive. Real big positive number minus 1, positive. All factors are positive, so this expression is positive. The derivative function is positive for values in that interval. And once again, the graph of the function is increasing. Now, how can it be that we have increasing and increasing here, and we seem to have a critical number at x equals 1? Now remember, a critical number is a number which makes the derivative function equal to 0, and that means that the slope of the tangent line is 0, so that graph has to be flat right there on our coordinate plane. Now let's see what happens graphically. It turns out that this is the graph associated with the original function. Notice that it's increasing here, and then it goes flat at one point, and then it increases from that point. Now this is kind of an exceptional idea, but it does tell us something, and it tells us that this function is a continually increasing function. It is increasing throughout its domain, even though it's flat at that one point. It is continually increasing. So it's not necessarily the case that f prime of x has to be distinctly positive for every value in the domain of the function in order for us to say that that function is either increasing or decreasing throughout its domain. Here we have the example of that situation. All right, let's consider a problem concerning the toy industry. We have a toy distributor, and one of the games has these characteristics. We have a cost function and a revenue function. And here's the cost function, here's the revenue function, and we know the relationship between cost, revenue, and profit. We know profit is found by taking revenue and subtracting cost. So for the revenue, we just take the expression for revenue, and then we subtract the expression for cost. That's all there is to it. We clean it up a little bit, and we have this for our profit function. Now, to discover something about the graph here, we take the derivative. So p prime turns out to be this, and now we think about the zeros in the p prime function. Now remember, p prime, if we're talking about profit here, then the derivative idea is the marginal. Remember in the last chapter we talked about marginal profit, marginal cost, marginal revenue. And that's just rate of change in profit. Rate of change of profit, marginal profit. So that's what this function is all about. How is that rate of change changing? Well, let's see. The zero here, the zero for this function is at, if I set this expression equal to 0, solve for x, it's real simple. It turns out that x is 3,000 games. Now that means if this is a critical point in the graph, then this point subdivides the coordinate plane into a couple of intervals. The interval from 0 to 3,000, and we're assuming here that we're dealing only with positive values. It only makes sense in a situation where games are being produced. So from 0 to 3,000, we have actually an increasing graph. This derivative function would be positive. And beyond 3,000, from 3,000 to, I think we're going up to about 6,000 as our domain here. But in that other region, it turns out that the graph is decreasing. You see the f prime function is negative, and therefore the graph of the profit function is decreasing. So we're losing profit, or we're in the best shape possible by selling exactly 3,000 games. We have maximized our profit at that particular point. Now that's how this idea of analyzing a function using its derivative is useful.